Welcome to this explainer. Today, we're diving headfirst into how the massive, powerful celestial forces of tides literally shape our coastal landscapes. Whether you're just looking out at a super calm sea or watching massive waves crash against the shore, you are witnessing an incredibly dynamic, constantly moving system at work. Let's get right into it. Our roadmap today takes a systems approach. We're going to cover 1. The mechanics of tides, 2. The daily tidal cycle, 3. Geomorphic change and sediment, 4. Classifying tidal ranges, and finally, number 5, global coastal case studies. All right, section 1, the mechanics of tides. Simply put, we really can't understand the beach until we understand the sky. Right at the very core of understanding coastal energy is a concept called the tidal range. Basically, this is just the height difference between high and low tide, usually measured in meters. And this one single measurement, it dictates the sheer volume of water pulsing against the shoreline, which in turn tells us exactly how much energy is being injected into the entire coastal landscape. Take a look at how lunar and solar gravitational forces dictate the energy here. It's like a giant cosmic tug-of-war. When the Earth, Moon, and Sun directly align in a perfectly straight line, their combined gravitational pull creates these massive tidal bulges, resulting in what we call spring tides. But on the flip side, when the Moon and Sun are sitting at right angles to the Earth, their gravitational pulls kind of counteract each other. When that happens, we experience much smaller tidal bulges, and those are known as neap tides. So the crucial point to grab hold of here is comparing these two extremes. Spring tides, happening with that aligned orientation, give us the absolute maximum tidal range, literally injecting peak energy into the coastal system every 2 weeks. Neap tides, with their perpendicular orientation, give us the minimum tidal range, delivering the lowest energy levels. It's essentially this rhythmic, bi-weekly pulse of planetary energy. Moving on to section 2, the daily tidal cycle. Let's zoom in from those giant lunar orbits down to a single day on the coast so we can track these oscillating currents in real time. A semi-diurnal, or basically twice daily tide, looks exactly like this. See that blue line? That shows how sea levels oscillate over a 12-hour period, from high water to low water. That means in a standard 24-hour day, a given location on the coast is going to experience 2 high tides and 2 low tides as the Earth rotates right into and out of those tidal bulges we just talked about. Also, definitely notice that orange line. That's the rate of depth change, and it peaks right smack in the middle of the transition between high and low water. The coastal system actually follows a super strict, predictable sequence. First up, the flood tide brings water in over a roughly 6-hour period, completely covering the foreshore. This peaks at high tide, which is the absolute highest water level. Following this, the ebb tide takes over, pulling the sea level back down over the next 6 hours, revealing the foreshore all over again until it finally hits rock bottom at low tide. Okay, section 3, geomorphic change and sediment. So how exactly do these daily 12-hour cycles physically alter the shoreline and drive geomorphic change? Well, a really critical concept to grasp here is understanding the timing of these oscillating currents. When is this energy actively moving material around, and when does it calm down enough to actually allow that material to settle? When that rate of depth change we looked at earlier hits its absolute highest, we get these incredibly powerful reversing flows of water called tidal streams. These streams are wild. They are easily energetic enough to transport fine, muddy sediment right in suspension. In fact, this constant churning and flowing is exactly why the seas around the British Isles almost always look beautifully murky and brown. The energy is quite literally suspending the landscape in the water. So if you've ever been to the UK and felt like you're swimming in a cold cup of English breakfast tea, well, now you know why. Conversely, we have a phenomenon called slack water. This happens for about 2 hours surrounding both high and low tide, when those powerful tidal streams just totally cease. This sudden, dramatic drop in energy inputs allows all that suspended fine sediment we just talked about to finally deposit and settle. And this is absolutely crucial for sustained accretion in stores like salt marshes. Basically, the baffle-like leaves of salt-tolerant plants physically trap the sediment, slowly but surely increasing the vertical height of the marsh over time. Section 4, classifying tidal ranges. Now that we've got a handle on the physical processes, like sediment transport during tidal streams and deposition during slack water, let's actually categorize this geographical data. Geographers love to classify things, right? So they categorize these energy pulses into 3 key ranges.
First, we have macrotidal environments. These are incredibly energetic, boasting a tidal range of over 4 meters. Then, mesotidal environments fall right in the middle, sitting between 2 and 4 meters. And finally, microtidal environments have a range of under 2 meters, meaning they experience far less overall tidal energy. Which brings us to Section 5, Global Coastal Case Studies. Let's take all this academic framework we've been building and apply it to real-world coastal systems to really see this geography in action. Starting off with a microtidal environment, let's look at the Mediterranean Sea. Now, despite being a truly massive body of water, it barely registers a tide. You might be wondering, why is that? Well, it all comes down to its geography. The incredibly narrow Strait of Gibraltar essentially traps the water inside. Most seawater just cannot easily enter or leave the Mediterranean as the Earth rotates, so you end up with very small amounts of tidal energy and a range of well under 2 meters. Now, on the completely opposite end of the energy spectrum is the macrotidal Bay of Fundy over in New Brunswick, Canada. Just look at the dramatic difference between high and low tide at this exact same port. It's mind-blowing. The Bay of Fundy actually boasts the world record tidal range. We're talking a staggering 17 meters, or about 55 feet, between high and low tide. The physical reason for this colossal vertical shift is, again, heavily localized coastal geography. The entire bay essentially acts like a giant funnel. As the tidal wave moves in, the coastline progressively narrows. Because that huge volume of incoming seawater literally has nowhere else to go, it gets squeezed tighter and tighter, forcing it to pile up vertically and creating an absolutely massive high tide. Now, heading over to Western Europe, which is generally a macrotidal region, we have the UK's Bristol Channel and the Severn Estuary. Very much like the Bay of Fundy, the geography here actively funnels water inland. This giant squeeze generates the world's second highest tidal range, hitting an impressive 15 meters. The sheer force of this is just staggering. Twice a month, timed perfectly with the spring high tide, this rapidly squeezed water creates a literal, massive tidal wave known as a tidal bore on the River Severn. This extremely energetic wave triggers intense geomorphic change. We're talking severe bank erosion, and it transports vast amounts of silt in suspension as it forcefully surges its way inland. As we wrap up this explainer, it is so vital to reflect on the real human impact of these incredible geographical forces. Back in 2004, the Morecambe Bay tragedy cost the lives of 23 Chinese cockle pickers who were caught at night by the lethal speed of fast-rising tides in a macrotidal zone. You see, these aren't just abstract textbook concepts. They are immensely powerful and sometimes very dangerous natural systems. So I'll leave you with this. Considering the rapid, extreme energy shifts in these macrotidal zones, how must our coastal management strategies, and honestly, our sheer respect for nature, adapt so we can safely survive alongside them? Thank you so much for joining me for this explainer today. I really hope it changes the way you view the coastline forever.